Okay, this is a launch for section 5.5 in Integrated Math 1, and this is just a quality little activity, so I thought I'd do a totally separate video for this launch. And you will want to have this coordinate plane right here for the activity. So if we were in class, I'd give you a hard copy of it, but you'll want to print this out from home if you're watching the video at home. Okay, so let's take a look at the launch. Starts right here, slideshow from current slide, and here we go. Okay, so for this problem, we're going to let x equal the number of adult tables and y equal the number of kid tables. So we have a constraint right here, cost. At Peter's Party Palace, any adult table will cost Peter $25. So this Peter's Party Palace is obviously a place where people go to celebrate birthdays and things like that, and it's one of those family style restaurants that has like games and stuff too, and you have adult tables and kids tables, and what you do is you reserve them, and an adult table costs $25 for family style food and service. So if x is the number of adult tables, then I begin this problem with 25 x's. All right, and then any kids table will cost Peter $10. So y is the number of kids tables, so let's go plus and then 10 times y. Peter can spend up to, and you guys know up to, that would be less than or equal to $1,000. Less than or equal to 1,000. And this is an inequality in standard form for the cost constraint to take a group of people to Peter's Party Palace. Now, we have another constraint, and it's space. So at Peter's Party Palace, an adult table takes up to 50 square feet. All right, so 50 square feet for every adult table, and a kids table takes up to 20 square feet. So how about we go 50 times x, the number of adult tables, plus 20 times y, the number of kids tables, and let's figure out how much space we have. The dining hall has room for up to 1,800 square feet. So again, up to, that would be less than or equal to 1,800 or 1,800. All right, and there is our inequality in standard form for the space constraint. Now, number one, write separate inequalities in standard form for both the cost and the space constraints above, which we already did. Look at us. So that's good to go. Number two, graph the boundary lines for each of these inequalities. So we're going to start just by graphing the boundary lines. All right, and that's what that piece of graph paper was that I had for you. So let's go there. And we're going to use intercepts to do that. And again, when we have standard form, we like to graph boundary lines with intercepts. So, and with that, I like to use cute little tables. So for the cost constraint, at the y-intercept, x will be 0, and at the x-intercept, y will be 0. So let's look at that cost constraint above. 25x plus 10y is less than or equal to 1,000. Now I'm going to get out my calculator. And now I'm picturing, if x is 0, I have 25 times 0, which is 0, and I'm left with 10y is 1,000. So to find my y, I'm going to take the 1,000 and divide by that 10. And you guys know 1,000 divided by 10, what are you going to get? 100. Shouldn't have even had to punch that out on a calculator, huh? All right, and now the x-intercept, y is 0. So 10 times 0 is gone, and you're left with 25x is 1,000. So let's take the 1,000 this time, and let's divide by 25. And I get 40. So the x-intercept is 40. Now let's do the same thing for the space constraint. So if x is 0, we have 50 times 0 is 0, and we're left with 20y is 1,800. So to undo this multiplication by 20, we're going to divide 1800 by the 20. So 1800 divided by 20, and I get 90 there. The y-intercept is 90. All right, now the y is 0. So the 20 times 0 is 0, and we're left with 50x is 1800. So let's take this 1800 and now divide by that 50. 1800 divided by the 50, and I'm getting 36 for an x-intercept. Nice. Now with those intercepts, I can do the graphs of perfect boundary lines with my piece of graph paper, a ruler, and a pencil. So let's do this now. The cost constraint. The y-intercept is 100, so let's go all the way up to y equals 100, and the x-intercept is 40. So I don't see 40, so what is these hash mark work? Is that 5, 5, 10, 15, 20, 25? Yep. So 30, 35, and 40. There it is right there. And then I get my ruler out, and I draw a solid line from the y-intercept to the x-intercept. And the line has to be solid because there's an equals right there. All right. If there was just a less than, I would do a dash line. Solid line right there. Now, for the space constraint, the y-intercept is 90. So what are these? These are going by 5s too, aren't they? So let's check it out. 75, 80, 85, 90. Right there. All right. And the x-intercept is 36. Well, we're going to have to approximate that one because we're at 5, 10, 15, 20, 25, 30, 35. So I'd just be just beyond that hash mark. And we're approximating right there. That might not be perfect, but we did our very best. And now we get our ruler out again, and we draw, do you see the equal sign? We draw a solid segment between the y-intercept and the x-intercept. So there's the two boundary lines. Perfect. All right. Now, number 3, list 4 ordered pairs that will work given both constraints. And then number 4, list 4 ordered pairs that will not work given both constraints. So back to our boundary lines right here. Now, we need to know what is the double shaded region in this system of inequalities. And the key is this, you guys. All right. 10y's here, 20y's here. You know, if I was solving for y, my last step would be I'm going to divide by 10, which is a positive number, so my inequality will not change. Here, my last step would be I'm going to divide by 20, which is a positive number, so my inequality would not change here. So I know that I have to be less than or equal to both of those boundary lines. So if I'm less than the red boundary line and the blue boundary line, that means I have to be in this feasible region down here, this little right triangle right there. I have to be on or below this blue, the lower boundary line. And then ordered pairs that will work. What did they say? Pick 4 of them. So I'm just going to pick 4 ordered pairs in this feasible region right here. And I always like to do them as simple as possible. So I'm going to use, it looks like, probably either the same x value or the same y value for each of them. So let's see if I use the x values. X is 5 right there. And then I can go up here, and then there, and there. And the reason I do this is because now when I do my ordered pairs, oh, and here's the ones that won't work, by the way, and I'm going to use 50 here. And these will not work because, by the way, I'm above both boundary lines, and the feasible region is this triangle right here, that right triangle. So these points out here wouldn't work. Put one there, one there, one there, and one there. And now you'll see why I did this. Ordered pairs that will work. I already know the x-coordinate of each of those, the ones I chose, were 5. And you could have used 10, 15, 20, whatever you want. And now let's just do our corresponding y-coordinates. Well, what's the y-coordinate of this first point right there? It's a 5. What's the y-coordinate of this second point? That would be 10. And then, of course, 15, and then 20. And now, look at the ones here, the ordered pairs that won't work. Well, the x-coordinate for all of those would be 50. And I'm using the exact same y-coordinates, 5, 10, 15, and 20. Watch. 5, 10, 15, and 20. That's a great little launch, and we're going to do some more stuff just like this.